Okay, welcome back. So now in the third hour for today, we would like to see how these solutions actually look like. So now we derived, in the first hour, we derived the stability equations. The second hour, we derived your Sommerfeld and the Squire equations. And now we would like to analyze those equations. So what can we actually obtain with those equations, and in particular with the results that we got. So what's the way of now calculating something? Well, we have this system here for V and eta with two operators, LOS and LSQ, so the Squire and your Sommerfeld operator, which essentially we need to solve an eigenvalue problem for. Well, so the whole principle is that once I know once the base flow, the base flow UB is known, so that may be the channel, the parabola for a channel, or that may be the Blasius solution for a boundary layer, or maybe something more complicated. For a wing flow with a pressure gradient. But once we know the laminar base flow, we can then formulate the Sommerfeld and the Squire operators. And we do that for each alpha, beta, and Reynolds number. So just go back to the definition of the Squire operator and the Sommerfeld operator. What we need to know here is, the base flow, of course. Then we need to know the Reynolds number, and we need to know alpha, and maybe a beta, which is hidden in the k squared. So we can then formulate the Sommerfeld operator and the Squire operator. Omega here has the function of an eigenvalue, so that will be the result of our calculation. So this we don't need to specify, that will come out. But all the other yellow quantities here, we actually need to specify upfront. So once we know the base flow, we select a few alpha, beta, and Reynolds, and we can formulate for Sommerfeld and Squire operators. Once we have done that, well, we can go like this. Then the second step would be solve the eigenvalue problem. Solve the eigenvalue problem. And we solve that for, well, what the result will be is omega, and omega would be the eigenvalue. And we will also get out the V hat, or the eta hat, when we also talk about the Squire equation, and that would be the eigenvector. And of course, in the context of our stability problem, the eigenvector would be the shape of our disturbance. So once we have all these eigenvalues, then the next step is we would like to determine the stability. Well, how do we determine stability? Well, we actually look at the growth rate of our omega. And if my omega has an imaginary part that is positive, well, then I know my solution is actually exponentially growing. And if the omega has an imaginary part that is lower than 0, it is exponentially decaying. So it's stable. So check the imaginary part of omega. And if I have omega I larger than 0, I have an unstable mode. And of course, that's exactly what I'm interested in. So I would like to know, do I have an imaginary omega larger than 0? Yes or no? If yes, I'm unstable. If no, I'm stable. So that's the sequence. I calculate the base flow, I formulate our Sommerfeld, I solve the problem, and I check my eigenvalues. That's the way a linear stability problem is always proceeding. It starts with the base flow, and at the end I check imaginary parts of eigenvalues. That's how it's being done. There's a few comments that I would like to make regarding that, because I said here I would need to formulate the problem for each alpha, beta, and Reynolds. Of course, there could be quite many eigenvalue problems that I would need to formulate. So there is actually a way of reducing the number of eigenvalue problems that we need to formulate. And this is, in particular, there's two relevant simplifications, or not simplifications, relevant considerations that we can make, where we will see that we, in fact, only need to solve for alphas, not for betas. So there's two main comments here. The first one I will do without proof, but it's not so difficult to show. But it turns out that only the Sommerfeld equation yields unstable eigenvalues. The Squire equations on its own will not give you unstable eigenvalues. So that means in order to get the unstable omega, it is actually sufficient. It's sufficient to look at the Sommerfeld equation, which of course in the end is just the equation for V hat, so the V hat equation. So what I need to do at the end is an eigenvalue problem, LOS times V being 0. So that is the problem that I need to solve, which translates then that the determinant of LOS is 0. So if it's only about stability, I do not need to care about the Squire equation. Of course, the physical reason is kind of the Squire equation is anyway forced by your Sommerfeld equation. So that is comment number one. The second comment is about the question: do I need to look at each alpha and each beta independently, or is there a way of maybe reducing the search space for unstable frequencies a bit more? And actually there is. So the question would be, is it sufficient to only look at 2D waves? So 2D waves would mean beta being 0. So is this enough? And actually it turns out that Squire in 1933 found a way of proving in a very simple way, in a very elegant way, that it's sufficient to look at 2D waves only. And this I will show you now. This is something that's called the Squire theorem. That he came up with. So the way to very quickly understand it is that we rewrite the Sommerfeld equations using the phase speed alpha divided by omega divided by alpha. So we introduce this C into the equation, which just gives me then, instead of the equation that I wrote above, gives me something very similar. It's just UB minus C times D squared minus K squared times V hat minus U prime prime V hat is 1 over I alpha Reynolds times d squared minus k squared times v hat. So this is just the Sommerfeld equation, exactly the same. It's this equation here, just rewritten using c, the phased speed inside. It's a very simple thing to do. The reason why this is interesting, or why this is important to do is, well, this one here is this is the Sommerfeld equation, but now let's look at the 2D Sommerfeld equation. So 2D, again, as I said, beta being 0. What does actually change in this equation? Well, UV minus C is the same, because in C we only have alpha. That's fine. D squared is also the same, but now instead of k squared, remember k squared was alpha squared plus beta squared. Beta is now 0, so this means now that in k squared, or instead of k squared, it would be this alpha 2d squared times. I mean the alpha that belongs to the 2d version of it. Then we have UB double prime times V, that's the same. And here we get 1 over I alpha 2D times Reynolds. And here it happens exactly the same thing. D squared minus alpha 2D squared times V hat. Okay, so just to remember, the above equation here is the 3D equation or Sommerfeld. And the lower one is the 2D version of it. Now, what you can realize is that the equations are very similar. It's only this term that changed, this term, and kind of these two terms changed. So I went from alpha to alpha 2. So that means if we somehow are able to match these terms, we will actually get the same solution for V. So if we do that, so we'll get the same solution if I match these, so that means if alpha 2D would be the same as K, and K was alpha squared plus beta squared, right? And I need to match alpha times Reynolds, which needs to be the same as alpha 2D times Reynolds. Well, actually, I should maybe call this Reynolds 2D and Reynolds 2D as well. Now this becomes interesting, because now I can solve this for Reynolds 2D, which is alpha divided by K, because alpha 2D is the same as K. So I get alpha divided by K times Reynolds. And obviously, because alpha divided by K is something that is lower than 1, I'll get alpha divided by K being times Reynolds being lower than Reynolds. So what does this mean now? Or what does this argument by Squire mean? Well, essentially it means that for each solution to the three-dimensional or Sommerfeld equations, there is the same solution for the 2D or Sommerfeld equations, but at a lower Reynolds number, right? Because Re 2D is lower than Reynolds. So let me write that down. So for each 3D or Sommerfeld solution, there is a 2D solution at a lower Reynolds 2D, well, which is lower equal than Reynolds. And the definition of this lower Reynolds essentially is this one. So that means in practice, if I just want to find out the lowest Reynolds number at which my flow becomes unstable, I know from this very simple consideration, it needs to be a 2D mode that has become unstable. Because if it was 3D, there would be a corresponding solution at a lower Reynolds number. That's what this means. So that means, in the end, if I'm interested at stability, for stability, it is sufficient to look at the 2D or Sommerfeld equation. So I do not need to calculate the eta equation, and I do not need to look at beta non-equaling 0. Okay. So 2D waves of or Sommerfeld equations are the most dangerous instabilities that you can have in shear flow. Okay, so now we have a recipe of how to what to do. Well, once the base flow is known, I formulate the Sommerfeld operator for each alpha and Reynolds. I don't care about beta anymore. I don't care about the Squire equation. So I can kind of take away the Squire equation, and I can take away the beta, because I know it's not needed. The second step is I solve the eigenvalue problem for omega and v hat. I don't need to solve it for eta because I don't have the Squire equation. So it's a 2D solution. And then at the end, I check what my eigenvalues look like. Okay. Now I would like to demonstrate that. I'd like to make a demonstration of this on the example of a 2D Poiseuille flow. So a 2D plane channel flow. Really the first example that we did together, the parabola in a channel. I would now like to look at the stability of that problem. So we think back, it looked like this. We had two walls, and there was a distance here, which was 2h. I had a coordinate system, which has its origin in the center, and the x direction was like this, the y direction was like that, and I had a mean velocity profile, that's what we calculated, which looked like that. So this is ub of y, so the parabola. So what I would like to do now is, I would like to calculate the instabilities that are present in this flow, and perhaps also finding out what is the lowest Reynolds number where this case becomes unstable. So my question now is, when or at what Reynolds number does this flow become unstable? And of course the parameters here are, well, we have ub, which is the parabolic base flow. And then we have the Reynolds number, which is the bulk Reynolds number, which we have realized that this is also connected to the mass flux that goes through the domain. So essentially it's the flow rate that I encode with the Reynolds number. And of course then I have another parameter, which is the alpha, because for the eigenvalue I still need to choose my alpha, which is the wavelength in the streamwise direction. So essentially I'm saying, okay, I'm looking at waves that have a specific that have a specific length, 2 pi divided by alpha. Stream-wise wavelength, wave number. Okay. So, do you know what the answer to my question would be? So, at what Reynolds number does this flow become unstable? Do you have any idea? So, Reynolds, I think we had some examples, or we looked at the Moody diagram at the time for pipes. I'm not sure I have it right now, but I can change anyway. So if we go back to so let me just do that quickly. So we have, if you go to the Moody diagram, this was pipe flow, but you can see here that the Reynolds number was around 2000 when it became unstable for pipe flow. So that means for channel flow, we would expect that the unstable Reynolds number would be somewhere there, 2000, 10,000, whatever. I mean, order of a few thousand. Okay. Of course, this is just a guess. Now we would like to actually see whether this is correct. So how do we do that? Okay. So I have prepared here a little MATLAB script. Can you see something? Not so much, huh? How do I make this bigger? So here maybe. Do you know how to make it bigger?
Maybe control zoom in with the mouse.
No, no, does not work. No. Maybe preferences. Fonts. Editor. So custom. So that's it. That's it. Okay, fair enough. So I did a very simple MATLAB routine, which I will also provide on the homepage, of course, and it does exactly what we now discussed. I set Reynolds, I set my streamwise wave number, and then I set also a parameter that relates to the resolution that I need to use. Then I define my D matrix. So in a discrete sense, the D operator will become a matrix. Since this is not a course in numerics, we don't need to really talk about how we do it, but just keep in mind that we now just formulate this D operator, the derivative operator, as a matrix. Then, of course, I make a D squared for the second derivative, and the D to the 4 for the fourth derivative. And then I'm formulating my Sommerfeld operator. And of course, now it's interesting to see or to convince you that this is actually the same. So this here is the one that we derived today. And if I'm now just looking at what I have, so it's a bit big, so maybe. So it's now not exactly the same order, but you recognize d squared minus 2 times d squared times alpha squared plus I alpha to the 4. that I here is not, that's the unit matrix. This essentially corresponds to the last term here, 1 over Reynolds times d squared minus k squared squared. Then I have this guy here, which corresponds to the second derivative of a parabola, which is constant. And then I have this term here, which corresponds to essentially this guy. So you have the d squared minus k squared, which is here. And then I have minus I omega, that's of course the eigenvalue, that's outside. But this alpha times diag, this is essentially the parabola that I have. So it's really the same, it's the same equation that we have derived here. And then what I do as the next step is I need to put boundary conditions. I have channel flow, so I have 2 boundary conditions on the top, 2 boundary conditions on the bottom. And then I'm just formulating an eigenvalue problem, and I solve it with I in math, as simple as that. And then once I have my my eigenvalues in omega and the eigenvectors in v, I just kind of post-process them a little bit, and I extract the leading eigenvalue, the one that has the highest imaginary part. That's the one that we don't like, that's the unstable one. And then I plot. That's it. So it's really exactly what we said. There's nothing weird in here. Yeah, so let's see what happens. So I just let it run. And what I get 3 different results here. I get first a spectrum, or something that I call a spectrum. That is the collection of all eigenvalues that I get. And here I will see now that, so here is 0 for the imaginary part. And if this guy is the most unstable one, if this guy would be above 0, it would be unstable. In this case, if you look at it, if you look at the value, it's minus 0.00248. So that means it's just about to become unstable. But right now it's still stable. And then, of course, because it's an eigenvalue problem, I not just get one eigenvalue, I get a lot of eigenvalues, but all of the other eigenvalues here are actually stable. So we don't care about that when it comes to unstability. And then figure number 2 and figure number 3 here, they will correspond to the eigenvector that corresponds to exactly this most unstable eigenvalue. And this here is now the shape of how the disturbance would look like in or my most unstable disturbance would look like. What you see here is the U disturbance and the V disturbance. So V is what I calculated for, and U is what I recovered using continuity. And what you see here in red is essentially that you have a high amplitude disturbance close to the wall, close to the lower wall, and also here with a negative sign close to the other wall. So that means you have a disturbance that has a wave-like character that has its maximum close to the 2 walls. And as I was saying, it's wave-like because it has an omega. It also has a real part here, 0.28175. So that means it actually moves in a wave-like shape. So it's a wave that passes by inside this channel. And if the Reynolds number is large enough, it would actually grow. And I can just show you that. This was now for Reynolds 5000 when it was stable. Let's just go in and do this for Reynolds 10,000 instead. We run it again. And what we will get is that, at least I hope that's what we get. Oh, it's still stable. Still a little bit stable. Maybe I should go to 20,000 then. Or wait, I need to be careful. It may actually be that this one is not, that this alpha is not unstable. Let's see. It's still not unstable. The imaginary part is still a little bit lower. Which I guess already now shows you one problem, because I need to know what alpha I'm looking at, which I don't know, because the channel may have any alpha. And now I just need to choose an alpha, which may or may not be good. And this is exactly a problem. So we need to actually make an optimization over all different alphas to find out which ones are really unstable. Therefore, I have prepared another code which exactly solves that problem. And so I'll show you here. And of course, also this I will provide you. What I will calculate is something that is called the neutral curve for channel flow. So that means it's the locus of all the points in a Reynolds alpha diagram which have zero growth rate. So essentially that's where we have the curve with neutral stability. And then I know if I'm on the right side of that curve, I have positive growth rate. If on the left side, I will have negative growth. And how I do this is essentially exactly the same as before. I will just create a mesh with a few selected points in Reynolds and alpha space. And in each of those points, I solve exactly the equation that I had before, the Sommerfeld equation. With the boundary condition, I do Eig, I extract the highest eigenvalue. And then, instead of showing the eigenfunction, I'll just do a contour plot of that to identify the neutral stability. Let me now calculate that. It takes a little bit longer because, of course, it has to solve the eigenvalue problem in a whole mesh. But this is the result that I get then at the end. And I think this is one of the main results from linear stability theory on channel flow. So we have here on the x-axis is the Reynolds number. So 0.5 here is 5,000, 1 is 10,000, and so on. And on the vertical axis we have alpha, so the streamwise wave number. And the black line here, that is the neutral stability curve. So that's the curve on which we have zero growth rate. And it turns out that everything outside of this curve is stable. So outside it has a lower growth rate than zero, so it means it decays. And inside this, it has a higher growth rate than zero, so it is amplified. And of course now my initial question was, what is the lowest Reynolds number at which my channel becomes unstable? And of course, that is now quite easy to see. You just go from the left and you see where I, for the first time, touch the neutral stability curve. And you see this red dot here? This here is actually the point which has the lowest Reynolds number at which the channel becomes unstable. And this actually is a kind of a magic number in stability theory, 5,772. And this goes back to a paper by Stephen Orszag in 1970, when he, for the first time, calculated exactly what I'm showing you here with a specific numerical method to get out this number. So the answer to my question was the channel becomes unstable at 5,772. Now, what did I do wrong before when I tried to illustrate to you how it becomes unstable? Well, my problem was that my alpha that I chose was 1.12, which is was just a choice. Now, of course, you see 1.12 is here. So I was essentially just going in the unstable, in the stable region. So therefore, it never became unstable. But of course, now you see, if I want to become unstable, let's just choose an alpha that is 1, for instance, and the Reynolds number of, let's say, 10,000. And it should be unstable. Just that you believe me that my code actually works, I do that now. Reynolds of 10,000, alpha of 1. And I run that again, and it is positive. So that means it has actually become unstable. And if I'm looking at the eigenvalue, it is actually slightly above 0. So it has actually become unstable. So with this MATLAB tools that I will provide to you, you can actually do exactly what we discussed now. You can formulate your Sommerfeld problem, you put in an alpha, and you solve it, and you will get a result for it. And as I was saying, you essentially get three different results. Now, this I would like to write again. So we get three different results from running that. Three results. The first result is what we call the eigenvalue spectrum. And the eigenvalue spectrum is what I need to improvise this, not improvise, but I need to try to capture that properly. So the first result is this one here, the eigenvalue spectrum. Just put that, take that, and I put that in here. So this is the location of all the eigenvalues that I get, which I can then use to identify which one of those is the most unstable eigenvalue. So in this case, it was of course this guy, which turned out to be the most unstable eigenvalue. So this is what I can get from the spectrum. And it turns out that there's a name for that most unstable eigenvalue, because there was, of course, a person that kind of predicted that for the first time, that these types of modes do exist. And this was first predicted by two people. They're called Walter Tolmin, who lived from 1900 to 1968, and Hermann Schlichting, Hermann Schlichting lived from 1907 to 1982. And of course, Schlichting, I guess you know from a book that he wrote, Boundary Layer Theory. It's a big book about all different aspects of boundary layers. But in honor of these two people, the most unstable eigenvalue, and in particular the flow structure that belongs to that, is called a Tolmin-Schlichting wave. Or, because Schlichting is a slightly difficult word to predict, to pronounce, it's also just called a TS wave. So whenever you talk about stability and you talk about a TS wave, you mean the most unstable eigenfunction from linear stability. That is a TS wave. Yeah, so this is kind of the first result that you get. The second result is the shape of the, well, let's say the shape of the TS wave, which is also sometimes called the wave function, because it gives you the kind of the functional shape of the actual wave. And also this we can get from this eigenvalue solver that I provide you. That's this one here. This is the second type of result, where it shows as a function of the vertical distance, you see how the amplitude of the velocity changes across the channel. And also here it's interesting that Tolmin and Schlichting, they predicted the existence of this wave in the 1930s. So just a little bit before, the war started, or kind of the National Socialists were taking over in Germany, and kind of research stopped. So they predicted it in end of 20s, beginning of 30s. But then it took another 16 years roughly until the TS wave was for the first time detected in an experiment. And this is also a very famous experiment by Schubauer and Skramstad. And this was published in 1946. So they did the first experimental verification of TS waves. And of course, nowadays, this is all very easy to detect in any lab. Okay, and then the third type of result that we get from all of this is what I showed you last, and that was the neutral. I typed it wrongly. Sorry. That was the neutral stability curve, which is the curve that tells you where and how that the flow becomes unstable. So that's the neutral stability curve, or just the neutral curve, as it's also called. So something like that. And of course, here you can now directly see that this line here, that would correspond to the critical Reynolds number, Rc. And in this diagram, so everything inside this curve would be unstable, and outside it would be stable. So unstable means that the imaginary eigenvalue, the imaginary part of the eigenvalue is larger than 0, and stable means it's lower than 0. And of course, this, oops, I missed it a bit, but this here would be the critical alpha, so the wavelength of the critical wave, or TS wave. And of the results that we talked about, Rc being 5,772 for channel, that goes back to Orszag in 1970. Stephen Orszag that predicted that for the first time. Okay, now there's one last thing that I would like to show you, and because there is, of course, now we talked about all these waves and so on, but there is actually a nice visualization of these TS waves, so that you can actually see how they look like. And I would just like to show you that kind of a visualization of that. And that is shown on this slide, which I will also provide you in the material. What you see here is a boundary layer where you have the inflow down here, and then you have a flat plate, and then at some point towards the outflow, the flow actually becomes turbulent. Because in a boundary layer, as you know, the Reynolds number is slowly increasing as you go downstream. So that means at some point you will actually pass from stability into instability. And now these yellow lines or sausages that are oriented in a spanwise direction, these are the TS waves. And as we were discussing, they're two-dimensional. just give me 1 more minute. So they're two-dimensional because we know it's the two-dimensional waves that actually become unstable first. Right? That's what we derived with Squires' theorem. So we have these waves that that then start to grow, and if you look carefully, you can see at some point they start to grow, so they become thicker, and then of course at some point they become thick enough, and then they become unstable and will break down. If you want to look at this also animated, because I was just saying that they were traveling and so on, this is an animation of how this would look like in reality, something like that. So you would really have them traveling, and while they travel, they would become, their amplitude would increase. So these are TS waves. They look like this, and they're characterized by the shape that we have had in, by this shape that we calculated. Okay. Yeah, I think this is all I wanted to tell you today about the viscous stability in a channel, how to derive the equations, and then also to solve it. I will of course provide all of this material, these slides, which is just a summary of what the MATLAB code does, and the MATLAB code's on the homepage. So if you want to try that out yourself, you can do that. And also with this, I would like to thank you for being here in presence. I will now go back to Stockholm, and we have another lecture on Wednesday, 9 to 12, which then will be, well, kind of the last full lecture, and then I have to see how much material is left for maybe the one in 1 week. But of course, as always, when you have more questions or anything that is would like more explanations, let me know. I'm happy to answer if I can. And other than that, well, thanks again, and we will see each other at the latest, I guess, in the exam at some point. Yeah. Okay. Thank you very much.